So I guess you suffered a little bit yesterday. It was very fast. For those who didn't know L2 Betti numbers, I will give a very small reminder. But first of all, in this Women's Day, I would like to emphasize the role of evoked in the theory of homology for groups. Indeed, both Pavel Alexandrov and Hans Hopf, in their memories, explain that during the summers of 26, 27 in Göttingen, they were lecturing about what they called at that time combinatorial topology, which is, I guess, the topology of simple complexes or something like that. And she immediately realized that they could use a group to track the chains or the cells. So why don't you use the group of algebraic chains, and inside that the quotient, the cycles, the boundaries, and take the quotient, and then you get a group, and all the invariants you need are there. Instead of considering incidence matrices, this is what they used to do. Incidence matrices in normal form, where you have integers on the diagonal, each one divided by the next one, and these kind of things. And find the finite numbers. Indeed, your finite numbers are just the function of an abelian group. Okay? So, in the situation, you have, let's say, a finite complex. Let's call it A. Okay? And I remind you, you have this top P. Let's consider the set of the algebraic group made of the sums, the formal sums of chains and so on. Okay, so till C0, and let's say 0 here. Okay, and so the homology then is compact. K is compact. There's finitely many cells in each dimension, and so you see with Z coefficients. These groups are abelian, finitely generated abelian groups. Okay, the kernel are the same of the same type. The images also, and so the quotient is a finitely generated abelian group. Okay, and a finitely generated abelian group has the form of, it has a torsion-free part, which is Z to some power. This power is the Betti number in degree n, right, plus the torsion part, which is, again, an abelian group. And the term torsion comes from this theory. Indeed, it has been introduced by Poincaré, because when he built the theory, he built it implicitly using Q coefficients, while if referring to Betti, it was more likely using Z coefficients. And the difference is on the torsion part. Then in his paper of 1895, Analysis Situs, he introduced the Poincaré duality, and Egard quickly wrote him and said, there is a mistake. Because, and he gave the example of the three-dimensional projective space, for which Poincaré duality does not work. But it works if you use Q coefficients. It does not work if you use Z coefficients. And Poincaré said, okay, the problem is only related to the fact that the manifold has some torsion. And so this finite groups or finite stuff appearing there has been called torsion after that. And now if you say a torsion group, torsion free, you refer to Poincaré indeed. Anyway, for Poincaré, it was not exactly groups, it was not like that, quotients of groups and so on. So it is really any writer, and she didn't write anything about that. Apparently, she was a very good colleague, explaining things for free.
Thank you.
So now let's come back to very quickly to what we said yesterday. So as you see here, we are considering compact stuff. And so what we did yesterday was, instead of considering a compact space, to consider, in a sense, its universal cover. So I called it L. Okay, and for L, you have also the space of chains, formal combinations of blah, blah, blah. Okay, of formal sums of cells of dimension n. Okay, and we soon pass from, let's say, homology with Z coefficients or Q coefficients to the Hilbert version, right? Remember, so now the cells are from a Hilbert base, and we said that here we have the boundary operators that are continuous operators between Hilbert spaces as soon as L is locally nice, or locally finite, and with a uniform bound. Okay, so usually we will take L with a free action of some group, such that this action is co-compact, and that this is realized. And I told you that there is this Laplace operator, which operates on each of those spaces, defined as, so here this is dn plus 1. So if you are here, you take the dn plus 1 star, then dn plus 1, sorry, plus, you take dn, and then dn star. Okay, so it's an operator, it's a positive operator from Cn to Cn. And the homology, the reduced L2 homology of L is isomorphic to the kernel of delta n. And then we suffered a little bit to give the sense, the meaning of dimension of that. Okay, a dimension according to von Neumann. Okay, good. And the way we did it was just to, well, consider the orthogonal projection from this space to the kernel and argue that it admits a trace, and the trace is well, is a good tool to define dimensions. Okay. So then, beta n2 of the action of gamma on L equals the gamma dimension, the von Neumann dimension of the kernel of delta n. And in case L is connected enough, the corresponding L2 Betti number of the group. So if L is n connected. Okay. So of course, it's not the case that every group admits such a compact L on which it acts freely and with some finiteness assumption. So this is where Figure and Gromov intervene. But I won't go into that, you can believe me that it works for, they can define that for L2 Betti numbers for every countable group. Okay? Good.
Sorry, that it is not true that every group admits such a thing, or it is true?
It is not true.
It's not.
For instance, if your group is not finitely presented, you cannot find an L which is simply connected and co-compact. Okay?
But if it is finitely presented, can we take a kilogram and fill in the holes?
Yes, this is a complex. This works. But then it is not necessarily two connected. It may have spheres in it.
So you fill it in?
You fill it, but you may need infinitely many,
Yes.
infinitely many points.
Oh, good.
And then it is no more. This is the case when you have your, if you take your telegraph and the group is not finitely presented, then you have cells. For each relation, you may have to add infinitely many orbits of cells, of two cells. And the same appears in every dimension. This leads to the notion of a group being of type Fn, finite classifying space up to dimension n.
But if it is finitely presented, no problem.
Up to dimension 1, yes. Or for a one connected, if it is
There is a group which is finitely presented, but there is a problem for two connected actions.
excuse me again.
Is there a group which is finitely presented, but you don't have an action on a two connected space, which is the
Not necessarily, you have an action, but it is not necessarily co-compact. You need a further finiteness condition in the next dimension, in the next degree. Each time it is more and more restrictive. And the gentle groups, like lattices in Lie groups, do satisfy these finiteness conditions. Und Fn satisfies this mapping class group also. Okay? But the nature is not only made of nice groups. It will just wave ends to tell you what we do with equivalence relations. So now you have a PMP equivalence relation on X mu. Okay. So first of all, something I did not say here. This dimension is computed, I said, using the projection. The projection, I told you, admits a trace because it commutes with the gamma action. And I said maybe just once that it belongs to the fundamental algebra of the group. Okay? The fundamental algebra of the group is the algebra of all those operators on L2 of gamma that commute with the action of gamma. For an equivalence relation R, there is also a fundamental algebra that's been introduced by Feldman and Moore in this two papers of 77. Okay. We won't go in the definition of that, but it's not very difficult to define such an equivalence relation, such a fundamental algebra. Okay. Just to remind you, we introduced the measure mu tilde on R. Do you remember that? First day. Okay. And the reason is that with that, we can consider L2 of R mu tilde, which is the analog of L2 of gamma. If your equivalence relation was given by an action of a group, then on R, it acts, the group acts on R itself. R is made of pairs XY. You can let the group act on the first coordinate or act on the second coordinate. You have commuting actions. And so you see it's the beginning, the starting point to define this fundamental algebra. Just that you also want to include L infinity of X. L infinity of X is an algebra, and the fundamental algebra of R combines, let's say, the group gamma, if it's given by a group action, this subalgebra of bounded functions. Right? Okay. So what do we do? First, we consider graphing. Right? A graphing is a measurable way to equip each class with a graph structure. This graph may have cycles. Okay, you can glue two-dimensional cells to carry these cycles. And of course, in a measurable way. Okay, doing that, you may have introduced spheres. You can try to glue two-dimensional balls to these spheres. Okay? So the higher dimensional notion is that of complexing. Okay? The graph is the one-dimensional stuff, and the complex is, so it's either CW complex or probably the more general it should be a CW complexing. This makes sense? Okay. And then each class now you have for each point X, so this is a graphing or complexing, let's call it sigma. So for each X, we first of all introduce phi of X. Now we have sigma of X. And so for each point, you have a complex. In that complex, you have the chains L2, the same as there. Okay? The L2 chains for each complex. And you have the Laplace operator leaf-wise in each orbit. Okay? And so you have the kernel of this Laplace operator, and you compute its von Neumann dimension using this mysterious von Neumann algebra, which admits a trace and so on. Yes?
The complex one, you guys completely complex or CW complex? No.
I don't want to make it precise. In defining the L2 Betti numbers, I did it with simple complexes. Okay. But it's much more comfortable to use geometry, and also it's more difficult to write with CW complexes.
Okay, but so it's not just like fill in triangles and
that, yes. But of course, in the graphing, it is not necessarily triangle that you have. So you need to add larger cells. And if you want to stay in the world of simple complexes, then you must add vertices. In doing that, you enlarge the space X in the sense so it becomes okay. Yes.
Is there any like a graph, like group that can you have the graphing? It also can have like complexity.
So it again, please.
So I think like not is all the graph like is all the group graphable? Like it's all the group like a misgraphing.
Yes, for every group you can find a graphing. A group is generated by a subset of elements of the group. Each, if you want, the graphing could be also, it is not necessarily locally finite, that's the point. But you see, the group is countably many, gives you countably many transformations of the space. This gives you a graphing, the collection of those transformations of the group, of the space, right?
The whole equivalence relation is a graph, right? All the elements.
Yeah.
okay.
Good. So you see, let's say the fiber was Laplace operator, its kernel. With all of this, you see, you have these strange notations. You know that you can take or is it orthogonal sums of Hilbert spaces, and if you have many of them until the point where their number becomes continuous, you have an integration. So okay, you all of them in a single Hilbert space, which is something like that. It's the way we write this. It goes back to von Neumann. It's okay. So it's just a continuum of Hilbert spaces. So you have to put measured structure on that. And what is an element of that? Let's write it sigma. Okay. It is just for each point, you pick an element for each point x. You pick a vector in this vector space, in this Hilbert space. And you want this section to be measurable and L2.
You want equivariance, right? You want whatever x sees and whatever some x prime in the same orbit or like class sees, that they agree on what they see, right?
Yes, but so
In the complex thing, like
yeah, yes, sure. This is why I defined this downstairs in a sense, using the graphing on x, and then for each point, the way it is defined, you see, for every x and y in the same orbit, the complex sigma x and sigma y are isomorphic, just the base points are not the same.
But do they have to choose the same chain?
No. When you integrate,
They completely forget that they're in the same. When you do the integration, they forget that they're in the same.
yes, just behind you have the action of the equivalence relation of the group. Just like there, when you take a chain, if you take elements in the same orbit, in the same gamma orbit, you don't ask for them to remember at the point when you define an element of the chain here, let's say. Okay, good. And so you can imagine that if you have a two-able group, which means that you can find, and the L2 Betti numbers, then you define like that L2 Betti numbers of, let's say, the complexing, the way we said it, okay? So we have complexing, Laplace operator, kernel, polynomial dimensions, and in case the leaves, the sigma x are unconnected, then what you get is independent of sigma. So it is invariance of the equivalence relations, okay? So it becomes Bn2 of R when sigma is n-connected. Well, when almost every sigma x is n-connected. Yes?
You said it needs to be L2, so you just take the norm of every function pointwise.
Yes.
This field.
Yes.
That's outside.
You like to
For this explanation, it needs to be locally finite. Because you need and this is a huge part of the work to extend it in general, and especially also to connect very different complexings. Yes.
Sorry, Damien, I have a question which is maybe completely shows you that I don't follow that well. So the question is, you could define a local Betti number with the kernel of the Laplace operator of nx.
Yes. And that one
do that. You somehow put the Laplacians together.
It's to the same thing. Yes. So in this condition, in this statement, you can define a local, which is what you have the projection, okay, and then you have chosen, let's say, the cells around the base point.
Yes.
Okay, and the cells around the base point give you a certain family. And one, I don't know how to call them. sigma. So you can say something like you take all the sigmas that are, it's something like that, that are adjacent to the base point x. You take this and then you integrate on x. This leads eventually to the same value.
So this says that the local Betti numbers integrate to the
Yes,
global Betti numbers.
yes. But yeah,
It's ergodic. Let's assume R is ergodic, then it's all gonna be constant. No, wait, no, let's just for a sec. Suggesting.
Because it depends on the degree.
No, but the numbers won't change because it's all isomorphic. I'm confused.
it's probably true. Yes, yes, yes,
It would be the same if R is ergodic.
yes, that's true.
It would be that number that we call it.
Yeah, and this is the way eventually you can prove that it coincides with those of the group in case,
3 PMP.
yes, it is a free PMP action. But you get that afterwards.
Mhm.
Okay. Good. Okay. Now, let me connect that to planes of subgroups. So, okay. Now, L2 Betti numbers. In the theory of L2 Betti numbers, there is an important theorem due to Luc, which is called the Luc approximation theorem. The situation is the following. You have a group gamma that is residually finite. It means the following. You can find inside gamma a decreasing chain, a decreasing sequence of subgroups, okay, such that the intersection of the gamma i's is trivial, and the index of gamma I in gamma is finite. Okay, so you can find finite index subgroups that eventually vanish. Okay, and in Luc approximation theorem, you know, overlap asks the gamma I to be normal in gamma. Okay, so this is the situation. And okay, moreover, let's consider a free action, sorry, on L, a simple complex. Let's say co-compact. Okay, so according, so associated to that, you have, of course, L mod gamma, which is a compact space, corresponding to the finite index normal subgroup gamma 1. You have L mod gamma 1, and this is a finite cover, right? And L mod gamma t, and you have a sequence of finite covers, right? And the fact that the intersection is trivial means that eventually you have the whole L upstairs, right? Moreover, here you have the action of gamma, since this is Galois coverings. Okay, so you have a sequence of actions of gamma, and in a sense, this converges, okay, to the universal cover with the action of gamma. Okay, and Luc approximation theorem answers the question of Gromov. How can we compare the Betti numbers of this finite covers with something here, which is the L2 Betti numbers? Okay, and in this situation, so Luc approximation theorem claims that if you consider the usual Betti numbers, or the n of L mod gamma I, and the limit is taken when I tends to infinity. So I is the index here.
So the Betti numbers of these sort of what topological spaces?
Yes, of course, you have simplicial complexes. And so this is the first part there. A compact, blah, blah, blah. And we have the Betti numbers here. Okay?
Forgetting that it's like comes from a homogeneous like mod gamma I.
Yeah. Yeah. If you remember the prior formula for free groups, you very quickly realize if this is a tree, if L is a tree, and the gamma is a free group, the finite index subgroups, you see all of this are graphs. Okay, and since the Euler characteristic is multiplicative in the index, you realize that the good normalization is by the index. So if you want something to converge, you certainly have to divide by the index. Thank you. So this limit is exactly the nth L2 Betti number of the action of gamma on L. Does this make sense? So here you have just standard Betti numbers of compact simplicial complexes. Okay, and this limit normalized by the index converges and to something that is well understood, the corresponding L2 Betti number. Is it okay? I guess it's something like 94. Good.
And potentially these events are easier to compute than because there is no Van dimension involved in this type of stuff.
Yes. It's not there. Okay. And so there are some situations where we can easily compute that and conclude something there. And also the converse happens, that we can compute this using Théories, using blah, 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 and then we conclude that symptotically something happens, something non-trivial happens. Okay? Okay. We can notice that we have several generalization of that. If we remove the condition that it is a nested sequence and blah, 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 we can, okay, so we have some results, for instance, independently, Albert and Lassie taught, and on the other hand, Alessandro Foray, myself, and Michael de la Salle, we have generalization of this in several directions. First of all, we had a generalization with Nicolas Bergeron, where we remove the normality. Okay, and if we remove the normality, and we proved that what we obtained are L2 Betti numbers of some complexing. So I will explain that. Now, if you have a sequence of groups like that, I thought corresponding to it, or maybe I can draw it here. So you have a tree associated to a sequence of groups like that, a nested sequence. Okay? First point is, well, gamma mod gamma 0. So this is 1 point. Gamma 0 is gamma. Then you have gamma mod gamma 1. Maybe here. Gamma mod gamma 1. Okay? And I draw a line like that. Then you have gamma mod gamma 2. And of course, every gamma 2 class belongs to a gamma 1 class. Okay? And you can continue like this forever. You get a tree and a boundary of the tree, dt. Right? On each level, you have an action of gamma. On each level, you have an action of gamma. Here, gamma acts in this finite set. Okay, by left multiplication. Here also. Here you have an obvious invariant measure. You have 3 points, the same atomic value here and there. And so you get a measure on the boundary. Okay. On the boundary, you have the induced action of gamma. Right? Okay. So what we proved with Nicolas Bergeron, so this holds even if the gamma i's are not normal. Okay? And so what we prove with Nicolas is, so without the assumption that the gamma i's are normal, in the end, we have this action on the boundary. Okay, so you consider gamma acting on dt times L. Now gamma acts diagonally on this, right? So this is a symmetrical complex, and this is a probability space. You can take the quotient. The gamma action on L is free, so the quotient is very nice, and you get exactly a complexing. Okay, complexings have L2 Betti numbers, and so we proved that in general, this quantity tends to the L2 Betti numbers of that complexing. This makes sense? Now there is a topological counterpart to that, which is due to Albert and Nikolov. When was it? 2012. Let's stay in the framework of Luke approximation theorem, a group and a chain of finite index subgroups, normal, and so on. Okay, there is a quantity that is very simple, a topological quantity that is the rank of the group. How many generators do you need to generate your group? So you take the rank of gamma I, and you ask how does it behave when you tend to infinity. Again, Schreier formula for free groups tell you that you should probably divide by the index. Okay, so you divide by the index, and you ask what is the behavior, the asymptotic behavior. So first of all, this is the chain, the sequence is clearly converging because it is subadditive. It is a subadditive sequence. Okay, so this convergence, it's quite easy. Right there, it was not at all clear that we had convergence. And Albert and Nikolov proved that this converges to the cost of the action on the boundary. Okay, so this is the cost of the action of gamma on the boundary, -1. Okay, when I tends to infinity. So you see, the rank is an upper bound on B1. It is always the case, okay? And you see that you have the analogous, so here you have a topological statement in a sense, while there you have an homological statement. Okay, yes?
Sorry, this result is with or without the normality assumption in the subgroups? It's not.
It is with the normality, let's say. Yes. Yeah. It is true more generally if you relax the normality, well, you have to you can say something more.
But it will only work in residually finite groups anyway. So
Yes.
Further sequences only exist in.
Yes. Yes.
Does this theorem with Nicola recover the approximation theorem when the subgroups are normal?
Yes, but we use the same techniques, so it's
If this
that the boundary of the previous set is the group with the finite topology.
I don't understand.
The boundary of the previous group, just like a copy of the group with the finite topology.
It is a finite group associated with the sequence. So it's not the whole profinite limit. Okay, but it is a profinite group associated with the sequence. That's true. DT is a group itself. In the setting when you have normal subgroups. Okay. So this is called the rank gradient. It has been introduced by Lakenby and used to study various properties of algebraic properties of groups, right? And so you see that here it becomes very important to establish whether this boundary action is free in Luc setting. Okay, so it becomes very important to establish whether the group has fixed price. Can you compute that? If the group has fixed price, you realize that this quantity does not depend on the particular chain you are considering. Okay, and I remind you this other problem: cost versus first L2 Betti number. Is it found that cost minus 1 equals the first L2 Betti number of the group? If this holds, you see that the topological version and the analogical version converge toward the same value, in degree 1 at least. And we have analogues of that. We are working on that with Miklos and Slobodan, a colleague from Rio, Théories. Okay? Good.
The rank gradient is the limit, right?
The rank gradient is the sequence. Yes.
Or is the sequence?
Yes, the gradient of the rank, I guess it's the sequence. Okay.
And sorry, so is the rank gradient associated with this particular sequence, right? It depends on the sequence.
Yes. Really, this gives you
non-fixed price.
yes, a non-fixed price statement. So you see, all of this is good. Now let's switch to. It's not exactly movies, since we have no popcorns. Eventually, no movies. But I will continue with some slides. Is it okay? So I saw some examples of provable groups. Okay, provable, I remind you, means that there is some free PNP action, and we can find a graphing that is a treeing, right? Maybe I use yes, full screen. That's good. Okay. Good. Examples: analog groups, surface groups, since there are lattices in isometries of H2. Okay, another example of a provable group is the fundamental group of such a surface. You take a surface of genus greater than 1 with one boundary component. You duplicate it, and you group them along the boundary component. Okay, so it's an amalgamated free product of three groups above these, right? Using or mimicking what we did for these branch surfaces, Gaussian, Twitter, and Wheaton or use that to show that elementary free groups are treeable. Okay, free products of treeable groups, amalgamated free products of treeable groups over finite groups, and something which is quite important, subgroups of treeable groups. Okay, if you have a fluid equivalence relation, you take a sub-equivalence relation, you can find a term for it. It's not so easy a priori, you see? So we did it independently with Jackson, Kekli-Trouveau. It was at about the same time, just they published it much later. Greg Yort proved that if you have a group with variable action, then indeed that action can be realized by an action of a free group, the free action of a free group, as soon as the cost is an integer number. Okay, is an integer. Okay, and this leads to this equivalence. A group is trueable if and only if it is measured equivalent with a free group. And we have 4 LE classes: finite groups, infinite amenable, free groups of finite rank, and the free group of infinite rank. Now what about strong probability? You guess what it means. Every PMP free action is. Okay, are there trueable but non-strongly trueable groups? And it was a long-term question about surface groups, and we solved it with Gromov and Tucker draw. And we showed that strong trueability holds for compact surfaces, compact branch surfaces, lattices in the isometries of H2, and these elementarily free groups. And I will give you an idea of how this works. This relies on planarity. Here you have the universal cover is made of planar stuff, glued along lines. Okay, so we use this planarity to solve the strong trueability. And so it relies on planarity and the following sub-foray statement. If you have a graphing phi, you assume that first it is locally finite, that the classes are infinite. Okay, and so now for each x, you have a graph, phi of x. A graph has a certain number of ends. It is the same here because of the first component. The number of ends is like in Oth theorem, either 0, 1, 2, or infinite. You cannot have finitely many, you cannot have 6 ends for the graph. This would select a finite piece, okay, and violate the first commandment. Okay, so if the classes are infinite and not two-ended, then you can find a subgraphing. It is no more connected, but it partitions the classes into trees with one end. Okay, and so this is a key.
Sorry, but if it's hyperfinite, it will remain connected, no?
Yes. So let's consider let's say a surface group. So gamma is the fundamental group of some surface. Okay, we consider a free PMP action alpha of that group on the one end. On the other hand, of course, gamma acts on the universal cover of the surface. Right? That is, let's say it's an hyperbolic surface. The universal cover is the Poincaré disk. Okay? And I can take a tessellation of this. It's not exactly a tessellation for, let's say, S2, because each vertex should have degree 8. But you can imagine that this picture would become immediately impossible to read. Okay? So you have to imagine a little bit. So this is a tessellated H2 on which the group acts. Okay, and now I take the diagonal action on x times SG tilde, right? So each sigma x looks like that. Okay? And you have the root here, or the root here. This makes sense? Okay, now we consider the dual tessellation. Okay? So we have the dual, let's write it something like that with a star. And of course, we have the action of x on SG tilde star. The one skeleton of this is a graphing of something. Okay? This graphing is not two-ended. It is infinite. So you can apply the subforesting statement. There is inside a subforest, the connected components are one-ended. They go to infinity, right? Now, what you do, so we started with the action with the green edges, right? And using this one-ended forest, we remove all the edges, all the green edges that are crossed by one red edge of the one-ended tree. Okay? And I claim that what remains is a treeing for the original graphing, is a subtreeing of the green original graphing. Why? Okay, so for instance, this edge has been removed, right? I claim that in the resulting graphing, they are still connected. The endpoints are still connected. Why? Well, this is the planarity. This edge, together with, crosses this red edge, it has a finite path. This finite path has a finite domain in the plane that is surrounded, by definition, by remaining green edges. Okay, so these 2 points remain connected in the simplified complex graphing. Similarly, there is no loop, because if there is a loop somewhere, this means that the points inside have no way to escape to infinity. Again, the planarity shows you that you must cross the boundary of the finite stuff, right? Of strong probability for surfaces and for their companions. Okay? So, what about now the higher dimension? So we know that we found a lot of groups that are treeable. There are plenty of non-treeable groups. And indeed, this is the real world. Groups are non-treeable in general. So, for instance, infinite Cardan property groups are known to be non-treeable for Y. This is due to Adams and Spatzier. Also, non-amenable direct products of infinite groups are known to be non-treeable for years, 23 years. Okay, and the more generally non-amenable groups with cost 1 or with 0 first L2 Betti number. I guess you saw that along the, if you are treeable and have cost 1, then I told you that you must be hyperfinite, thus amenable. Okay, and since subgroups of treeable groups are treeable, a group that contains a non-treeable group, of course, is non-treeable itself. For instance, if you take a free product organization of three groups, in such a way that this Z goes to a non-trivial proper power, then you see it contains a non-amenable group plus 1, even here. So for that, you need, let's say, P is greater than 2 and Q is greater than 3. Then it is non-amenable. Okay, so this group is no more treeable. While if you build a surface group, it is treeable. So according to the way you put the z's in the free groups, you get either treeable or non-treeable groups. This makes sense? Okay. And so we have a notion of geometric dimension for groups. Standard definition, well, more or less standard. So let's a group act on simplicial complexes, and you ask, well, let's say properly, so with finite stabilizers, and the question, what is the smallest possible dimension of such an L being contractible? Okay, so this defines a dimension. So for instance, for Z to the D, the dimension is D. You let it act on or D, simplicialized, right? Now the ergodic dimension for a free PLP action or for an equivalence relation is, well, the smallest dimension of a contractible field sigma x of complexes that are contractible. Okay?
So for free groups, it's 1, right?
Yes. For free group, it is 1. And the ergodic dimension is the smallest ergodic dimension over all its free PMP actions. Let me tell you right away that we have no example of a group with 2 actions of different ergodic dimension. Okay? And this is essentially the single lower bound for the ergodic dimension. It is L2 Betti numbers. Okay, since L2 Betti numbers are computed for equivalence relations and for groups using contractible simplicial blah blah blah, if this complexing has dimension smaller than D, then you cannot find a non-zero D L2 Betti number. Non-zero L2 Betti number in dimension D. That's clear. If you have nothing, this is 0. The quotient of the kernel is 0. Okay? So, if your group gamma contains a subgroup with non-zero D L2 Betti number, then the ergodic dimension is greater than D. Okay, so this shows, for instance, that the product of free groups, non-abelian free groups, okay, the ergodic dimension is D, and strongly, because I remind you the current formula, all the Betti numbers are 0 except in dimension D, and moreover, such a product of groups acts on the corresponding product of trees that have dimension D. Okay? A product of free groups acts on the product of trees, and the dimension is D. Well, random groups, ergodic dimension for ut Fn, for instance, is 2n minus 3, because, well, the free ut Fn contains some poly-free group whose L2 Betti number in degree 2n minus 3 is non-zero. What about such a product of free groups and Z? Now all the Betti numbers vanish because of Q-net formula, and Z, they all vanish, everything disappears. Okay, but it contains this. So the dimension is at least D, and indeed it is D plus 1. Because of this result I got with Camille. So if the top dimension, I mean, if in degree D, the Betti number of gamma is 0, and it contains a subgroup for which it is non-zero in degree D, then the ergodic dimension of gamma must be greater. It is a trick, really. This paper is not difficult. Once you know a little bit the theory of L2 Betti numbers, it's a nice trick. Okay, this implies so that the ergodic dimension of this product is D plus 1. This implies that the top dimensional L2 Betti number of ut Fn is non-zero. This is a counterpart or a result back from this theorem in well, the establishment of L2 Betti numbers for groups. Also, if M is an aspherical manifold of dimension 3, and its L2 Betti number, aspherical means, okay, the universal cover is contractible, we take its fundamental group, subgroups. Okay, so these subgroups must have vanishing L2 Betti number in degree 3 first. Okay, but since such a group is measure equivalent with a group of dimension, of proper dimension, the geometric dimension, the non-co-compact lattices are dimension 1 less. Okay, and then the same result applies that beta here is 0. Okay, and we know that the dimension is not greater than 2. This implies that the subgroups must have vanishing L2 Betti number in degree 2.
I mean, can you put that for a second? Do you mean to put the reversing equality for the second bullet point? Is it less than or equal to b plus 1?
Yeah.
Yeah.
No, if this is 0, then the ergodic dimension must be greater. So the result, if the ergodic dimension is d, then the diff L2 Betti number must be non-zero. Okay, this implies you have dimension greater than d, and if it is 0 in this dimension d, then the ergodic dimension must be even greater.
Oh, and then we get equalities because of other
Yes.
inequalities. Okay, okay.
I'm sorry if I was not. Okay, I almost finished. Now, if you have an aspherical manifold of dimension 3, you can play the same game we did with surfaces. Except now you have a manifold of the dimension 3, cellulated, and you have the dual graphing. Okay, in the dual graphing, it's like a globe you put, you can find a one-ended subforest. It's like a globe you put inside your manifold, and you remove all the three-dimensional cells that you cross, and all the corresponding two-dimensional cells you remove, removing the globe. And what remains is a complex of dimension 2 that is connected, simply connected, and connected. Okay, so this implies this. So either you are amenable or you have strong ergodic dimension 2. So what about if you are provable, then this implies that the second L2 Betti number is 0. But by Poincare duality, then the first L2 Betti number also is 0. So you are provable with 0th first L2 Betti number, you are amenable. Does this make sense? Okay, and more generally in higher dimension, we have this kind of stuff. And of course, since we saw hyperfiniteness, an equivalence relation that is an increasing union of finite sub-equivalence relations, we can also consider the approximate or ergodic dimension. So you write your equivalence relation as an increasing union of sub-equivalence relations, maybe of smaller dimension. And so the dimension, so for instance, for Z, it has ergodic dimension 1, but it is hyperfinite. The finite ones have ergodic dimension 0, thus the approximate dimension of Z is 0. Okay, so this is another invariant. And here we have examples of groups, for instance, this kind of groups. They have some actions that are not approximable, non-trivially. So the approximate dimension is d plus 1. And if you take a product action, then the approximate dimension decreases by 1 using the z part, which is hyperfinite. Okay, and so maybe I stop here. Oh no, I have problems, questions. So you have to think in that for the problem sessions. What are the ergodic dimensions of Sn and Z? It's an open problem, even for Sn, 3 Z. Could be either 2 or 3. of the fundamental groups of closed hyperbolic manifolds and groups with non-strong ergodic dimension. And I stop here.
Questions? Yeah, so these one-ended forest and treeability results all did use PMP, right? So you don't have it for not PMP actions that these are treatable?
No, it's much more difficult for non-PMP.
So like the Stalin's ones there, the roots of ergodic dimension one, I can characterize them.
I cannot hear you, I'm sorry. Somebody could repeat or?
Is there like a Stalin's ones there, for groups of ergodic dimension one? So can you characterize them as like, you can measure?
I'm saying like Stalin.
Can help me?
Is there a Stalin something?
Oh, Stalins.
Yeah.
Stalins theorem. Oh, yes.
Not just Stalin's, yeah, Stalin's what theorem?
So like swan, I can measure equivalence.
Oh, Swan.
Measure theory dimension one.
Yeah, so Stalins one is that having chronological dimension one implies being
Is that like?
so in a sense, you see, being trueable with the result of you are measure equivalence with a free group. That's all. This is the York theorem. This is the best one can do. This York theorem, you have so the paper, the original paper of York, and you can also have a look at the paper of Ben and Anush, where they get even better results, but recover your theorem.